Hello, linear algebra students. Math 2318, excuse me, working on section 5.4. Here are three more examples, 3, 4, and 5. Hopefully will help you understand the section. So in these, we're going to assume that the two vector spaces, V and W, are exactly the same, and that they're both already Rn. Okay, so we're going from Rn to Rn with a mapping T sub A that just takes vector x and multiplies it on the left by a matrix A, a usual linear mapping. Okay, and we're also going to assume there's only one basis in play, some basis beta, so that when we do the coordinate mapping from x to its coordinates with respect to beta. Here's a little aside. If you recall from section 4.4 on pages 220 through 221, if you want to review over here, if beta is a basis with with vectors b1, b2 through bn, basis vectors, then the coordinate mapping that goes from x to its coordinates with respect to beta is the same thing as multiplying on the left by a matrix there called P sub beta inverse. The reason that's the one is because the way they found these coordinates on page 220, 221, you can go back and look and see that. The way they found these coordinates was by solving this system of equations. Just put some unknown here. They solved for this, and those were the coordinates. So since multiplying the solution, these coordinates by P sub beta gives you x, and since P sub beta is invertible, then you can say that the coordinates of x with respect to beta are just equal to P beta inverse times x. So that's why we have an inverse right over here. I'm missing an inverse. Let's see, where did I put that marker? Here you are. Yeah. So right here, that should be an inverse there. Okay. So using beta, you get the coordinates with respect to beta by multiplying by this matrix. And as this is another copy of R sub n, and we're just using the same basis beta, the same thing will happen to anything over here. It will also be multiplied on the left by P sub beta inverse. Okay, but now if you look over here, okay, so the same setup that you saw in examples 1 and 2 in section 5.4, this kind of graph where we're saying that if you take x, map it to a sub x, and then map it here, and that's going to be by multiplying on the left by this, you should get the same thing if you take this first through the coordinate mapping and then over here. If there is some matrix M, which your book likes to notate this way, okay? Some matrix M so that M following P inverse of beta, so in other words, multiplying by M on the left of this brings it over here. That should be equal to this, which is what we got by taking P sub beta inverse and multiplying it A sub x and multiplying it on the left by P sub beta inverse. Well, if that is true, that's only going to be true if this equation is true, and that equation is equivalent to this one, is equivalent to that one. Take any form you like, it's all saying that M, if such a matrix exists, it has to be similar to A with respect to that basis beta. Okay? And in the columns of P sub beta will be those basis vectors beta. Okay. Well, that's a formula we could use to compute to see if such an M exists. Basically, we can see that it exists because all three of these existed, so we just need to find M. And so I've worked out some numbers here for you. you'd like to try this example and then stop the video. Let me give you the information here. So this is your example 3. Try this with, so here's the matrix A that does a nice transformation of R2 to R2, right? It rotates things by pi over 6 in a counterclockwise direction. Those are its entries. So that's just some random matrix you've seen before associated with the transformation. And here's some basis I came up with, whose numbers will be a lot nicer for you in the future because a few fractions right there. Using this and this, come up with p sub beta inverse, and then that product to get m. So you could stop the video now, try that now, and later in the video, when you come back, you'll see the answer, what m would be, okay? Now you'll notice that even though this is in section 5.4, this type of transformation doesn't have any kind of eigenvector, right? The only thing that stays invariant under a rotation is the 0 vector, and the 0 vector can't be an eigenvector. So everything I've said up to this point is quite possible without any eigenvalues or eigenvectors, okay? So that's one thing. All right, stop the video, go off and do this problem. You find m. All right, let's say you've come back. What are the other kinds of problems that you're going to see that you've been seeing in 5.4? Let's see if I can get this to a better angle. Oh, that's a little too much, isn't it? Okay, how about that? Alrighty. So, okay, you can read that. So, well, what if instead of being as nasty as that m that you just found was not diagonal, was it? It was very ugly. What if m could turn out to be a diagonal matrix? Oh, by the way, here's the m you should have found in example 3. There's a solution. Check. If instead of being such a nasty looking matrix, not very pretty, if instead it's a diagonal matrix, then look what we have. A is equal to p beta times d times p beta inverse. In other words, A is similar to a diagonal matrix. Well, that's the definition of being diagonalizable, right? And if you remember from the previous section, we had a bunch of results about the beauty of diagonalization, is that if A is diagonalizable, then the columns of P are eigenvectors of A. And the diagonal entries of D are their eigenvalues. And they go, remember, the columns of B are in some order matching up with the order of the eigenvalues along D. Try it. Here's a much nicer matrix A. The questions are asked in this very simple form that are actually asking you to do a bunch of other things. So if they say, here's a matrix, find a matrix form of it, a similar form of it. This is their way of saying the matrix M, right? That is diagonalizable. By saying that, that should cue all of this result, and you should go, oh, well, let's find the eigenvalues and eigenvectors. Well, but to answer this question, actually, all you really need to do is just find the eigenvalues and put them in that way. If you do find two, like you have here for this example, the eigenvalues are distinct, then you know you're going to be able to find linearly independent eigenvectors to put into P sub beta, okay? So here they're not forcing you to find all the eigenvectors. They're just hinting, seeing if you understand these relationships and this theorem, to realize that when they ask the question this way, you have to go find the eigenvalues of A. More complicated question would be if they said, given A, same matrix as here as in example 4, find a basis beta such that T sub A with respect to beta is a diagonal matrix. Yes, that's much more, because now you have to go and find you have to go and find all those eigenvectors as well as the eigenvalues. So I've left that as an exercise for you. There is an answer. Remember, many possible answers when somebody's asking for a set of linearly independent eigenvectors, but that's one of them.